Okay, welcome. We are going to be getting into a new topic that I'm super excited about. It's a topic that is something that is kind of near and dear to my heart. I have a bit of a story about Laplace transforms in that when I learned them myself, learned them is a stretch, but in my second year course, the differential equations course that I took when I was a student, we did this topic as a very last topic in the class, and it lasted a couple of days. I didn't learn anything. I thought it was stupid. I didn't understand it at all. It seemed bizarre. I didn't understand the point. And yeah, I basically took the big L when it came to answering anything on an exam to do with Laplace transforms. And it wasn't the kind of L that we're going to be dealing with here. Um, yeah, and yet, when I got my job, when I first talked to the dean, and he asked me, "So, do you teach differential equations?" I You have to answer yes when somebody offers you a job. Like something that I've always wanted was teaching, and so I was going to say yes to this question. And inside my brain immediately went to, "Oh my god, I'm going to have to teach Laplace transforms and I don't understand them even a little bit." And I knew I had to learn them. And the next summer, when I was building my notes and I was coming up with the course and so on, I sat down and I figured it out. And then I realized just how amazing this topic actually was. That it's really cool, it isn't that bad. I built a set of notes that I would have wanted when I was a student to help me, uh, I don't know, really master the topic. And I think I built something great. I think I have because time and time again, this has been students' favorite topic, and that definitely wasn't the case when I was a student. Laplace transforms are really cool, and I hope you'll enjoy the journey with me. So, what the heck are these things? They are an integral transform. An integral transform. That sounds scary right from the start. But essentially, it's going to be some sort of an operator that acts on some functions to give new functions. And those new functions are going to have some amazing properties in play that help us to transform differential equations into things that don't look like differential equations. We're going to be able to solve differential equations without ever taking a derivative or integral or any of that stuff, because it'll all have been done in the process of taking the transform. And so you'll end up learning a few rules to go by, and that will be enough. And it's pretty neat, okay? This is what the transform looks like. And again, this is going to look really scary, but we're going to work through a bunch of these. So we say that L of f of t. So you're given some f of t, some function of time. You're taking L of this. This script L is kind of a beautiful thing, and it's really fun to draw. I'm going to draw it lots, and you're going to be like, wow, I want to make L's like Matt makes. People say this every year, and they're just script L's. I don't know, but they're very fun. People will be like, I don't know. I've had people that have literally filled their page with L, 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 and so on, and it's the strangest thing ever. But people just love these things. So, yeah, decorate your test papers with it if you want. I don't really care. But here's what it is. It's an integral. It's an improper integral. It's the integral from 0 to infinity. And what you do is you take f of t, that function you're taking the Laplace transform of, you smack it with an exponential, e to the minus st. Don't even know what s is here. It's some parameter that's going to kind of be not... It's going to take the place of t in some sense. It's going to become kind of a new variable that your new functions are built with. Because when you hit it with this e to the minus st, you then integrate over t, which then does some stuff with the t and leaves you with a function of just s. Interpreting the s, almost, I don't want to say it's pointless, but it's very strange to try and attach some meaning to it. So I just want you to think that all that this Laplace transform does is process some function of t and gives you something out in terms of this new variable s. That s does have some representation as like I don't know, a quantity to do with like the frequencies of functions, the arguments of different functions, and so on. But we'll see We'll see exactly how that plays out as we get to some examples. Again, nothing to freak out about right now, and we'll get through this together, and you'll feel good about it. Okay, improper integrals. They only make sense if they converge. So we need that this improper integral converges, and the following criteria guarantee convergence. So we have to have that the f is piecewise continuous. You probably learned once upon a time that continuity implies integrability. So that's a great word. Integrability. 6 syllables, and I don't know, it's really fun to say. So, but you need that continuity in order to guarantee that an integral makes sense. But you also have to have one other thing. If you look at the functions inside that integral, I have an exponential with a negative number upstairs, provided that the s is positive, I suppose. But that exponential decreasing, in order for the integral to converge, you might think of, in terms of first year sort of thoughts and so on, you need that integral has finite area under it. And if you're integrating between 0 and infinity, that's an interesting thing, right? I need to make sure that, okay, I have a negative exponential multiplying something, so it's going to be, making sure that the resulting function tends towards 0 as t goes to infinity. That needs to be the case, because if it tends towards anything other than 0, the height of the function inside, the height of the integrand, the size of the integrand, if it doesn't tend towards 0, there's no way that I'm going to get a finite amount of area as the t grows really, really large. So one way to make sure of that is to make sure that that function, that f of t, doesn't grow faster than the e to the minus st shrinks. Right? If the f of t is larger than the e to the minus st is as t gets very large, then it's going to be the one that dominates the exponential. And you're not going to get that the height of the function goes to 0, and you're not going to get that finite amount of area. You're not going to have a chance of it. Okay? Essentially, you can't have that f of t grows any faster, so no more quickly, than an exponential. Of the form e to the at. So that's encapsulated here. The size of f of t is less than or equal to some constant times e to the at. Okay, for t greater than or equal to m, so it's an eventual thing, because we're thinking of t going to infinity. T has to be very large. So there has to be some point at which the function doesn't grow any more quickly than an exponential. And that is the other key, to make sure that this thing does converge. And if these two hypotheses hold, the Laplace transform of f of t exists on some interval of s values. And we're going to see that in play as we take the Laplace transform of a few familiar functions. Okay, so that's what we're going to do. We're going to take some Laplace transforms of basic functions, and what we're going to do is craft a set of rules to go by. So, Laplace transform of a constant. What does this look like? What do these things even look like? What should we expect? All right, well, let's do something really straightforward to begin with. What if f of t is just 1? What's the Laplace transform of 1? 1 is a fine function, right? It's just a constant. Okay. To take the Laplace transform, I'm going to do exactly what I wrote on the last page. I'm going to take that function. There's the 1 right here. I'm going to hit it with e to the minus st, whatever that represents, and then I'm going to integrate this between 0 and infinity. Okay, well, this is just an exponential. It's with respect to t, so I'm treating s as a constant here. I get minus 1 over s e to the minus st, and I have to evaluate this between 0 and, well, how did this work again? For improper integrals, usually what we would do is replace the infinity with some thing, b, and let the b get really big. So I'm going to replace this by a limit. The limit as b goes to infinity. I said, screw you, equal sign. I'm writing this there instead. So I'm taking the limit as b goes to infinity of this thing. And how do you do that? Well, you can fundamental theorem this thing. And if you do, well, let's see. Well, the b goes to infinity. That's being applied to the t. Minus 1 over s is going to be constant as far as this is concerned. So actually I can kind of factor that out and think of oops, maybe I'll write the limit as b goes to infinity. Minus 1 over s comes outside. And I have e to the minus sb minus e to the minus s0. So I'm just being honest. I'm just doing what I always do when I integrate. We'll figure this out after. One step at a time. E to the 0, that's 1 all the time. Okay. E to the minus sb. B is going to infinity. And if b is going to infinity, then this term goes to 0 as long as s is greater than 0, right? If s is positive, I get e to the minus something as that something gets really large, and e to the minus something really large goes to 0. So this part goes to 0 as long as s is greater than 0. Remember on the last page I needed some interval on which this thing converged. And so that's a little bit important. I need to find some interval on which this expression even makes sense. And for s greater than 0, it does. Then I get the convergence, because under those circumstances, I end up with, well, minus 1 over s. I've taken the limit now, so I'm getting rid of the limit. 0 minus 1. And that turns out to be 1 over s. And I'll put a box around that because this is the Laplace transform of 1. And we've found our first Laplace transform. We have a rule. I want you to think of it like that. The Laplace transform of 1. See, it's so fun to draw those swoopy L's. I highly recommend that you just do it. It's therapeutic in this time of difficulty. The Laplace transform of 1 is 1 over s. And the note at the bottom just speaks to that idea that we have to find some interval on which the integral even makes sense. If we are, we're good, and then you just don't worry about it. Okay? Good stuff. So we've got one Laplace transform of a very simple function, but let's move on. Example 1, find the Laplace transform of 1. This is what we would write. Exactly what I wrote on the last page. The Laplace transform, so if f of t equals 1, then you would say capital F of s equals 1. Well, you could write a couple of different things, right? Some people might write just capital F of s because the new thing you get is a function of s. I often like writing L of f of t because then I think of it as like, okay, I'm applying the Laplace transform operator on this function and getting out a new function. In either case, you get out 1 over s. Okay. And as I said, I referred to the Laplace transform as an operator. That's exactly what it is. We talked about linear operators earlier when it came to derivative notation, the big D notation, and it's an operator because it's something that you put a function into and you get out a function as a result. And the same thing goes with this, right? I'm putting in an f of t from a certain class of functions, and I get out some new function. So you can really think of the Laplace transform as being an operator. And because it's defined by an integral, and we know how integrals work, we have that, well, think about it. We have that if I integrate, I'm just going to kind of write this on the side, a c1 f1 plus c2 f2 with respect to something, right? dt, I guess, I don't know. We know that we can bring constants outside of integrals. We know that we can break up integrals like this. c1 times the integral of f1 plus c2 times the integral of f2. We know that integrals are linear in this sense, right? we have this property. And if you have a specific designated, if you integrate from 0 to t, for example, and 0 to t, I guess in that sort of case, you should not have an integral with respect to t. You should have some integral with respect to a dummy variable. So I guess I could do that. But the point is, I'll put an s and an s and an s. I shouldn't put an s because that's our special Laplace transform variable. I'll do tau. Tau and tau and tau. In any case, not important, not important. All I want to demonstrate is that an integral, we know that we can break up in this way. We can bring constants outside. We can take sums of integrals and integrate each piece. The Laplace transform is a linear operator. That's the whole point. It's defined by integrals that we know work in this way. And therefore, multiplicative constants. Multiplicative constants, by definition, can move inside or outside linear operators. We can move them inside or outside of the transform. So we just found what the Laplace transform for 1 was. It was 1 over s. And you should repeat it to yourself. And you should practice until you just know them so you don't have to look them up, because that's really key to being comfortable with this whole thing. We're going to now realize that we've actually found the Laplace transform for all sorts of things. The Laplace transform of -3, L of -3, by the theory that I just wrote down, I should be able to move the -3 outside multiplicatively. And it's the same thing as -3 times the Laplace transform of 1. It's got to be, because it's a linear operator. This is the same as -3 times 1 over s, which is -3 over s. So not only did we find the Laplace transform of 1, we found a Laplace transform of any constant. And so I'm going to write that down to the side. So the Laplace transform of k, where k is any real number, is equal to, it looks like k over s. And I'll put a box around that because we've got a related rule to the first one. Okay? So we've done constants. Why don't we check out some other kinds of functions then? Seeing that the Laplace transform is defined with an exponential inside that integral means that maybe it's not so hard to find the Laplace transform of an exponential function. And that's what we're going to do next. So suppose that f of t is e to the at, where a is a constant. Okay, so we're now going to take the Laplace transform of an exponential. I'm going to do what I did before. I'm going to take that function. I'm going to multiply it by e to the minus st. I'm going to integrate from 0 to infinity. And we're going to see how we do that. How do we do this integral, though? Again, you're treating s like a constant. We're treating a like a constant now, too. And I see two quantities with the same base here, and I can add the exponents. So that's what I'm going to do to start. This is the same as the integral from 0 to infinity of e to the, well, let's see here, a minus s t. Thinking of how exponent rules work, that should be not a huge surprise. Okay, I'm just adding the exponents and I factored out t at the same time. Okay, I have e to the constant times t. There's no problem integrating that. It's going to be e to the a minus st dt. No, sorry. And I have to adjust by that constant that's in front of the t. So I need a 1 over a minus s right here. And I'm evaluating this between 0 and, b, where the b is getting really big. So I'm going to take the limit as b goes to infinity of this thing. 1 over a minus s I recognize as being a constant because we're dealing with t values here. It was an integral with respect to t to begin with. So, and then we're going to just plug things in and see what happens. So I have the limit as b goes to infinity. We have 1 over a minus s. And then we have e to the a minus s times b minus e to the a minus s times 0. Okay, well, e to the 0, that's 1. And e to the a minus sb, as b gets really big, again, as long as the constant's negative, then that piece has to go to 0, for sure. That happens, so this goes to 0. That's necessary for convergence as long as the s is bigger than the a. So I'm going to say as long as s is greater than a. And again, we just needed to find some sort of values where this integral converged, and it looks like it will for this. So let's take this up and finish this off. I will have taken the limit there. I have a 1 over a minus s at the front. I have a minus 1 right here. And I can apply the minus 1 simply by swapping the order of the a and the s. So I would get 1 over s minus a. And we have a new rule. The Laplace transform of e to the at is equal to 1 over s minus a. And I'll put a box around that too. See, we're forming a set of rules. Because in practice, when you're taking the Laplace transforms and so on, you're not actually doing these integrals. These integrals are like the first principles definition of a Laplace transform. And you can evaluate those first principles definitions to see what happens. But once you know what happens, you can then use the rules. Because from now on, if you see what's the Laplace transform of e to the at, you can write down, well, it's 1 over s minus a, whatever the a is. You know now that a constant has, if the constant is k, the Laplace transform is k over s. We know that now. We don't have to do the integral. We're almost forming a set of rules, kind of like you have for derivatives or for antiderivatives. And Laplace transforms will work in a really similar way. Once we have that set of rules, we can go and play with them all day long. Okay? And they're actually pretty cool toys to play with. So let's do a couple of examples here. Find the Laplace transform of e to the minus t. Well, the Laplace transform, I'm going to write it this way again. If f of t, I think it's just useful to write it in a variety of ways because you'll see it written this way a lot of the time. And I want you to be used to it, no matter what language your profs are speaking in. So if f of t is equal to e to the minus t, then capital F of s is equal to the Laplace transform of e to the minus t, which is equal to, well, let's think about it. That's e to the minus minus 1 times t, right? That's what I want to write. Minus 1 times t. And that's equal to 1 over s minus the minus 1. So it's 1 over s plus 1. And that's what the answer is. Of course, in practice, I wouldn't write 4 steps to get there. I would see e to the minus t and be like, oh, it's e to the at is 1 over s minus a, so this is 1 over s plus 1. And it becomes that simple. It becomes that straightforward, I promise, especially when you practice lots. Okay? One thing that I did say it a few minutes ago, but it is important, I think. It's really important to practice with these Laplace transforms until you just know them. You're going to be able to look them up, right? Like, that's going to be a thing. We're going to have all of these rules. You're going to get to the test. You're going to have these rules on hand as long as we're in this COVID situation. And, you know, you're going to be able to utilize them. Actually, it's not just in the... I've always given students a list of Laplace transforms even for tests. But I've always encouraged students that you're not prepared to do this stuff until you have a very natural knowledge of... Imagine if you had to look up a table of derivatives every time you take a derivative. Imagine if you didn't know that the derivative of x squared is 2x. And you had to be like, well, let me go consult a table first. Walk, 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 walk. Rustle, 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 rustle. Flip, 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 flip through the textbook. Aha! There's the formula. Now I'm sure that the derivative of x squared is 2x. Let me write that down. Oh, shoot. Product rule. Yeah, you don't want to do that. That's so bad. And it slows you down. It makes you less confident. And what you need to do is practice, practice, practice until you just have them down. If you don't do this, you're not going to be as prepared as you want to be. I'm telling you because I've taught this course like 10 times now. And from my experience, my own experience, where I said that I had no idea what was going on, when I was taught this stuff, I was given a table of some different Laplace transforms and was told to apply it to differential equations without much explanation at all. We've done as much background stuff now as we ever did when I was a student. I'm not kidding. So, in my own experience, getting this stuff down meant learning these rules, committing them to memory, and being able to use them as if they were derivatives. And that's kind of what makes it fun, because people like rules to follow when it comes to math anyway. With regards to life, we'll save that for another conversation. Okay, anyway, that was a nice little talk there, but we have more examples to do. So we're going to do the Laplace transform of 1 again, but this time we're going to think of 1 as e to the 0t. Okay, so the Laplace transform of 1 again, but this time thinking of 1 as e to the 0t again. That's really interesting. All right, well, the Laplace transform of 1 is equal to, all right, that's weird, the Laplace transform of e to the 0t. That's what we're trying to say here. Hey, look at this. If we take the Laplace transform of an exponential, we know that it is 1 over s minus whatever this number is right here. That number right there is 0. And we get 1 over s minus 0, which is 1 over s. I want to kind of reframe what I said here, right? Instead of saying L of 1 equals this, I'm going to start with the exponential, say, hey, if you take the Laplace transform thinking of this thing as an exponential rather than a constant, you get to 1 over s, which you know is the same as the Laplace transform of 1, right? So I'm going to write, which is the same as the Laplace transform of 1. As it should be. One thing that's super cool about Laplace transforms, and well, I mean, you'd hope it would be this way, but is that they are very consistent with one another. They work together, right? You can think of these formulas as being compatible with one another. 1 over s is a kind of 1 over s minus 0, just for the right value of, it is a 1 over s minus a for the right value of a when a is equal to 0. It makes perfect sense. But it has to work that way, or else it wouldn't make sense. And we're going to see a few examples of that going forward. We're going to see that when we do the next kind of Laplace transform, which is the Laplace transform of trig. But we're going to do something wild with that. We're actually going to plug in some knowledge, so that we're going to revisit Euler's formula and use that to derive the Laplace transform rather than go to the integral. Though you could go to the integral too. But we're going to save that for the next video. I want you to sit, absorb this stuff, make sure you have these first couple of formulas down, as well as the basic definition of what a Laplace transform is. And I just hit my elbow on the table, and now I have to go nurse that to health before I do another video. So I appreciate your attention. Send kind wishes to my sore elbow right now. And I really hope that you enjoy Laplace transforms as much as I have come to. There's a lot more in this conversation to come. So we'll pick it up with that next lecture. So see you then. Bye, everybody.